Okay, we are going to leave the two-dimensional world of parametrics and move into the two-dimensional world of vectors. But I'm going to need you to change your calculator from radian mode, from parametric, into degree mode for vectors. So vectors is most commonly used in physical science, or physics, and so we'll be operating in degree mode here. So we're going to talk about some of the vector vocabulary. If you're in a physics class or have taken physics, some of this may be familiar to you. I know you talked some about vectors in your pre-calc and ham classes, and we'll talk about how that relates to velocity and acceleration as well. All right, so let's stick with 2 dimensions. A dimensional vector, a 2-dimensional vector, is denoted with the triangular brackets, like that, the angled brackets. So when you see that, you know that we're talking about vectors. A and B are the components. A is the horizontal component, or the X, and B is the vertical component, or the Y. So if A and B are positioned in 2-dimensional space, then the vector AB in component notation is what it would take to get to that position. That's called standard representation, always in relationship to the origin. The magnitude, or sometimes called absolute value of a vector, is found similar to the Pythagorean theorem, similar to the hypotenuse of a right triangle. Our book uses these single brackets with the triangular inside, okay? But that's not the most common. The AP, the College Board, is going to use the double. I prefer the double because it distinguishes it from absolute value. And so you'll commonly see that double bracket when you're reading College Board stuff. So just be familiar with both of those notations, and it's always the square root of the A component squared plus the B component squared. So just be familiar with the different notations. Magnitude is what that means. All right, the direction angle of a vector always is a non-negative angle, so we're always going in a counterclockwise direction. We'll never be going in a negative direction, and also always formed with the positive y-axis as the initial ray. So we might say that that is the angle if we're in quadrant 1. But if our vector is in quadrant 2 or one of the other quadrants, try that again. Okay, the direction always, okay, so it's not this direction, okay? First of all, it's going the wrong way, and secondly, it's not going from the positive x-axis, so that would not be correct. It's always from the positive x-axis going in a counterclockwise direction. That's the standard representation for the direction of the vector. Okay, so just quick practice. Find the magnitude and the direction angle for the vector with a -1 x component and a rad 3 y component. So it always helps me to visualize it. So I'm going to put this into quadrant 2, -1 and rad 3 here. So our vector is heading right there. Okay, so the magnitude of the vector is pretty easy to calculate. So that would be the square root of the component -1 squared plus the component rad 3 squared. So not too hard. 1 plus 3, so our magnitude is 2. Now we want to think about the direction angle. So our direction angle would be going in that direction. If you think about trig and a right triangle with a length of -1, rad 3, and a hypotenuse of 2, that's a 30, 60, 90 triangle. So So we've got 60 degrees in here, which means our direction, theta, is 120 degrees. So just use a little trig to help figure out the direction. Okay, it's more common that you'll go the other direction, that you'll be given the component form, you'll be asked to find the component form given the direction angle and the magnitude. So again, we'll try and picture this with a 40-degree direction angle. So 40 degrees, about like that. And we know that the magnitude is 3, which would translate to this. And so we want the component form. So we'll just use a little 30, 60, 90, excuse me, use a little right triangle trig to come up with this. We know that the sine of 40 degrees is going to be y over 3. And the cosine of 40 degrees would be x over 3, which is going to give us our component vector. So the x component would be 3 cos 40, and the y component would be 3 sine 40. And we can generalize that for pretty much any component vector. So the component vector would always be the magnitude times the cosine of the direction angle, and then the y component would be the magnitude times the sine of the direction angle. So that will help simplify if you're looking for a general component form. You may have heard of something called the head minus tail rule. This is if you're not starting at the origin. If you're starting at something other than the origin, so at x1, y1, and then you have a different terminal point, you can reorient that by subtracting the head minus tail, so the terminal minus the initial, and then like move that down to the origin, and all of the properties of the vectors would stay the same. So if you had, say, your initial point was 2, 5, excuse me, the initial point, let me write that correctly, and the terminal point was 4, 9, then the vector representation of that would be 4 minus 2 and 9 minus 5. So the vector representation would be 2, 4. That's the head minus tail rule. There's a lot of things that are kind of common sense about vectors. You can add components together. So if you're adding two vectors, you just add the x components to the y components. You can distribute scalar multiplication. So you can take a constant k and distribute. That only works with a constant. Okay. We are not going to do vector multiplication. We're only going to do scalar multiplication. Okay. -1 allows you to subtract vectors. So you would, instead of subtracting, you'd multiply the second vector by -1 and then add them together. So just for practicing some of those operations, 2u plus 3v means I'm going to have the scalar multiplication on u, so 2, -1, 2, plus the scalar multiplication on v. So that would give me -2, 4, plus 12, 24. And so we end up with the resulting vector of 10, 28. Okay, that's pretty self-explanatory. The subtraction, okay, we would end up with -1 minus 4 and 2 minus 8. So we'd end up with -5, -6. Okay, now C is a magnitude question. So we first have to find half of vector v. And so the magnitude of half of vector v would be 2, 4. So there's the half part, and then we find 2 squared plus 4 squared. So we're looking at 4 plus 16. So the square root of 20. So that's a magnitude of 2 rad 5. Most vector operations are preserved. It's commutative, you can add in any order. It's associative, you can group vectors with parentheses. The 0 vector doesn't change anything. In number 4, 2 vectors can cancel each other out. The scalar multiplication of 0 would result in the 0 vector. The identity multiplication of 1 would result in the identity vector. Again, associative property in number 8, distributive property of a scalar in number that's number 8, and then distributive property of a vector, number 9. So all of these things are pretty much self-explanatory. There's nothing surprising about vector operations. Now let's just go to how this affects calculus and how we're going to define that. So a position vector is defined in terms of time. So we have the x component and the y component. The velocity vector is the first derivative of each component. So dx over dt and dy over dt. The speed would be to compute the magnitude of the velocity vector. So find the velocity vector first and then do the square root definition for speed. Acceleration, a second derivative with respect to t. Now direction of motion. Now you're going to take your velocity vector, vector v, and divide it by the magnitude value. So this is going to be a constant. So you're going to take your velocity vector and take its components and divide it by a constant. So these are the definitions you'll be working with when you solve some of the application problems in terms of vectors. So let's try a couple. Okay. So one common physics problem is to find out how wind as a vector would affect something that's already in motion. So we've got a plane flying due east, that gives us our direction vector. 400, that gives us our velocity in still air, and then the wind comes along. So let's talk about our plane first. So we've got the plane velocity vector. It's going due east. Which means 400 is the x component, okay, pushing us in a positive direction, and the y component is 0. It's flying due east there. It's not intending to go anything to the north or to the south. But we've got a wind that comes across, and it's going 50 miles an hour, but it's got a direction of 60 degrees north of east. So we need to come up with the components of the wind. And remember, we've got the velocity times the cosine to come up with the x component. So we're going to have 50 times the cosine of 60 degrees. And then the y component would be 50 times the sine of 60 degrees. Now you can simplify those because we do know what the cosine and sine of 60 degrees are, but we don't have to. It may be an awkward value, which would give us a decimal. So you may, if it is simplifiable, you may, or you can just leave it this way. And so we want to know what the new ground speed of the plane is and the direction if you add these two together. So the resulting vector would be the addition of these two. So 400 plus 50 cosine 60 degrees, and then 0 plus 50 sine 60 degrees. To find the speed, okay, we'll go back and we'll check out Speed is defined here now as the magnitude of the velocity. So we have the velocity vector, and now we need to find the speed. So the speed should be the magnitude of the resulting velocity that we just figured out. And so this would be the square root of 400 plus 50 cos 60 degrees squared, and then 50 sine 60 degrees squared. And then you just evaluate that with your calculator, which results in 427.2 miles per hour. Now this is going to give the plane a new direction. It's not going to be flying due east anymore. It's also not going to be flying 60 degrees north, but it's going to be flying somewhere in between those two. So we want to figure out the new direction. So it, again, always kind of helps me to have a visual here. So imagine we've zoomed way in, and we know that our x component is 50 cos 60 degrees, and our y component is 50 sine 60 degrees. Sorry, I forgot the 400 here. And so we can find theta using an inverse tangent relationship. Which we get in degrees, 5.818 degrees as the direction now that the plane is flying off from due east. All right, so it's a little bit, it's no longer flying due east because of the wind. All right, let's move on to another common vector problem, and that would be how gravity affects something. So wind is a very common one, but gravity is also a very common question as it relates to vectors. So let's give this a try. So a baseball is hit with a 50-degree angle and a speed of 110 feet per second. And then if gravity is acting on that, let's find the resulting vector of those two. Okay, so we've got we need to figure out just the baseball. So assuming there was no gravity, what is the baseball's velocity vector? And so we know the speed is 110, and then the cosine of 50 degrees, and then its y component would be a speed of 110 sine of 50 degrees. So that's without any gravity acting on it. All right, so now let's bring gravity into the equation. Slide over a little bit. First of all, we know that gravity acts, downward, pulls down, and so that's going to affect the y component. And gravity is an acceleration value. So it has no impact on the x component, but gravity would have a negative 32. We're in feet here, so feet per second. And so if you were in meters, you'd have negative 9.8, but in feet, negative 32. All right, so now we need gravity's velocity. And so we're going to use antiderivatives. We've got 0 for the component, for the x component, but the y component would then be negative 32t. Therefore, put the two together, okay, and the resultant velocity is the combination of those two. So we're looking at 110 cos 50 degrees, which is irrational, and then 110 sine 50 degrees minus 32t. We also need the resulting position. Of the ball. And so we can use antiderivatives again. So 110 cos 50 is a constant, and so the antiderivative of that would be 110 cos 50 degrees t. And then the position vector 110 sine 50 degrees, that's a constant, t. And then the antiderivative of 32t is 16t squared. Now I know we've got plus c for all of those, but constants aren't going to affect the vectors. So yay, we don't have to remember plus c. All right, so we've got our resulting vectors. That was enough for that slide. Now we're going to move on. Okay, now the player leaps in the air to catch the ball 8 feet off the ground. And so that is related to the position of the ball. And because the player is leaping to catch the ball 8 feet, that's a vertical distance. So we want to take the position y component only and set it equal to 8. So that means I'll be setting 110 sine of 50 degrees t minus 16t squared equal to 8. And we're going to let our calculators solve that. You can solve it by graphing. Some of you have a built-in quadratic solver. You could use that. I'm always defaulting to graphing, so I would graph 8, and then I would graph and figure out. Now there are 2 places where 8, so if you're using a quadratic graphing program on your calculator, you might get this first one, which would be the first time that the ball was 8 feet in the air. But we want to get the second solution when it's coming back on its way down. And so solving that with an intersection, or however you want to end up solving that, we get t equals 5.1698, or if we're going to round correctly, 5.70 seconds. Now I want you to store that in alpha A or something on your calculator, because we're going to need that again. Now the question is, how far is the ball from home plate? Now we're talking about the position x coordinate, or the x component. So we're going to take that time value, 110 cosine 50 degrees t, and we're going to plug this time value in your alpha A plugged directly in. So we're going to multiply 110 times the cosine of 50 degrees times t. And I get 365, I think. Yep, 365.542. And that is how far the ball is away now from home plate in a horizontal direction. Finally, how fast is the ball traveling at this time? So now we're talking about speed. So we need to get our velocity vector. So our velocity is 110 cosine 50 degrees without the t. It's also 110 sine 50 degrees without the t, but minus 32. Now we do have that t value. So again, my alpha will come into handy when I want to plug in alpha A into that. And so if I'm finally looking for how fast, I want the magnitude of this velocity. So I will be setting up 110 cos of 50 degrees, that whole quantity squared, plus 110 sine of 50 degrees, minus the 32 times, and then you'll put your stored value in of 5.170. That whole quantity squared. Now make sure you use all your parentheses correctly and that you're squaring the entire quantity that you need to square. And if you do it right, you should end up with 107.648, and the units on that are feet per second. Now that might not, let's put that into context of how we might better understand how fast that's going. So if I multiply this by 3,600 seconds per hour, and then I divide that by 5280 feet per mile, I'll be able to convert this into how many miles per hour this is actually going. And so we end up with 73.396 miles per hour. Okay, that's a pretty fast ball for this person to jump into the air and catch. All right, so those are some sample problems working with vectors and their velocity, acceleration, and position. Just remember you're separating the components here, and so you're looking at x and y, the horizontal and the vertical, independently of each other. All right, so we'll come back together Thursday and we'll work through any questions that you've got on vectors. Some of you, if you're in physics, this may be easier for you. If this is the first time you've seen some of this, then it may take a day or two for you to feel like you're getting the hang of it. All right, so I'll see you Thursday.